So here's a summary of what we'll be covering in this project today. We'll start with a brief introduction to the inverse design method. Then we'll be looking at a couple of axial turbine nozzles designed using conventional stacking methods such as radial and compound lean, and evaluate their aerodynamic performances using CFD analysis. Then we'll see how the same nozzle can be designed with a unique type of stacking, which we refer to as controlled stacking, using the 3D inverse design approach. Then we'll look at some more aero performance analysis and discuss the benefits of controlled stacking compared to other conventional methods. And finally, we'll wrap up with some concluding remarks. So let's start with an introduction to the idea behind the inverse design approach, which we use throughout this project. And as you can see in this workflow, these are the inputs that are used by the inverse design method to give us the final blade design. So apart from some basic parameters, these blade loading inputs are flow related. So once you have a good understanding of your specific flow issue, whether it's profile loss or tip leakage or shocks that you are dealing with, it's possible to come up with guidelines on the optimum blade loading to tackle each of these issues. And actually this know-how has generality, which makes it suitable for all your turbine applications. And so what's interesting is that you only need to rely on your knowledge of flow physics, and then this method works for you regardless of your turbine size or which specific speed regime it falls under. And this makes the entire process very intuitive and removes any empiricism that is commonly seen with the conventional design methods. Now let's look at the design of turbines in a bit more detail. So across the specific speed range, turbines are subject to various flow phenomena and loss mechanisms which are dominant in that particular range. For example, as you can see in this specific speed chart, leakage and secondary flow effects are more dominant in the lower ranges, whereas shocks and profile losses take priority in the higher ranges. And in fact, with inverse design, it's possible to come up with a set of optimum design guidelines based on these fluid dynamic considerations of reducing the dominant flow losses for your turbine. However, when it comes to high and intermediate pressure stages of axial turbines, the loss mechanisms are dominated by the secondary flows or passage vortices near the hub and shroud end walls. Now, the design of HP and IP axial turbine nozzles, such as those used in the early stages of aero engines and land-based steam and gas turbines, is a complex problem because while conventional stacking methods like compound lean can suppress the passage vortex development near the end walls, but it increases the loss around the midspan, and this also makes the flow exiting the nozzle highly non-uniform, which in turn can increase the downstream mixing losses and also require modifications to the downstream rotor to be able to match this non-uniform flow profile. And that's why traditional methods often involve inefficient geometrical trial and error in trying to achieve control of the nozzle exit velocity, which of course consumes a lot of computational time and resources. So the question is whether it's possible to come up with a rapid design technique which can perform all of this in a single design iteration, that is, which can suppress the dominant secondary flows but without adversely impacting the midspan region, and also the exit velocity distribution in your axial turbine nozzle. And this is what we aim to explore through this project.